Cool. So I will get started on retrieval and retrieval augmented generation. So if we look at the standard way that we prompt language models, what we do is we combine a prompt template with an input, like I mentioned in the prompting class. So we could say something like, please answer this question. I think Vin Diesel has been a voice actor for several characters in TV series. Do you know what their names are? I hope nobody here actually knows this. Does anyone? No? Okay. I'm actually surprised, but very, very good job. The collective wisdom of this is comparable to ChatGPT. So with respect to pop culture, and presumably more with respect to a lot of other things. So but the problem with this is we have things like accuracy issues. So number one, we can have knowledge cutoffs. Large language models are usually only trained for a certain amount of time. Sure, they can be continually trained over new data, but once they're frozen, they'll only know things up till that point. Also, private data. There's a lot of data that's not available on the internet, not included in training mixes for large language models. So they'll be missing all of that, obviously. And also learning failures. So even, our very largest of models are still only about, let's see, they're only about 800 gigabytes. And you can't fit the whole internet in 800 gigabytes, no matter how hard you try, right? So they're going to be missing some of the information, in various places on the internet, even if they were trained on all of it. So another issue separate from accuracy is verifiability. So I'm sure everybody who has used ChatGPT has been in the situation where you get a very convincing looking answer, but you have no idea whether it's correct or not. And that's a problem if we can't go back and verify it. So a solution to this is retrieval augmented generation, or RAG. It wasn't originally called retrieval augmented generation, but that's kind of the standard name now. But the way it works is basically we retrieve relevant passages efficiently, and then we read the passages to answer the query. So, we have a big document base. We have a query. We do retrieval of some variety. We get a whole bunch of passages, and we read them with a language model and get an answer out here. So here's an example. This is very small, so I'll read it to everyone. I think Vin Diesel has been a voice actor for several characters in TV series. Do you know what their names are? Please list all of them. So ChatGPT sometimes supports search, sometimes doesn't support search. It kind of depends on the time of day and the feeling of Sam Altman about whether he wants to be doing that or not. I don't know. But when I ran this, ChatGPT was in its supporting search mood. So it basically gave me this answer. And it said, Vin Diesel lent his voice to several characters across various TV series and shows. Here's a list of characters he's voiced. Groot. So congratulations. I commend you on your knowledge of this. Santiago in Arc, the animated series. Dominic Toretto in Fast and Furious Spy Racers. Additionally, though the website for Big Mouth lists Vin Diesel, it appears to be a misunderstanding or an error, as Nick Kroll is credited as the voice of Vin Diesel in that show. So I don't know what that means. And then these roles showcase Diesel's versatility and contribution to voice acting. So this looks pretty good. Another thing that you'll notice here is that it actually gave you quotes. This is a little bit weird, right? Like, I don't really know what that means. What about these other ones? Has anyone seen Arc, the animated series, or Fast and Furious Spy Racers? Fast and Furious. Yeah. So this isn't actually correct. So you're right that there wasn't an animated version of Fast and Furious Spy Racers. So what I wanted to point out is, like, the only reason why I knew this, because I'm completely, I'm not very good at pop culture, is I was able to click on the links and actually read this and see that this was a mistake because it pulled things from places that weren't TV shows and where it wasn't Vin Diesel being an actor. But at least I was able to go in and verify it. So anyway, RAG consists of retrieval and reading. And so we can talk about retrieval methods and reading methods. I'll do retrieval methods first. Retrieval, of course, is useful not just for RAG. It's also useful for human consumption. We use Google search all the time, other things like that. So I'm going to talk about retrieval not just in the context of RAG, but also as retrieval itself. But we'll talk about RAG at the end. So retrieval methods. We have sparse retrieval. We also have document level dense retrieval and token level dense retrieval, cross-encoder re-ranking, and black box retrieval. So all of these are pretty widely used. Black box retrieval is, using some variety of this, but it's basically through an API and just getting the result from the API and using it. So we don't really know what's going on under the hood, but it's still pretty commonly used in research. And actually, I believe at this point when I queried this, ChatGPT was actually using Bing to do its search. So even OpenAI would be willing to do that. So first, sparse retrieval. So sparse retrieval, basically what we do, this is equivalent to the bag of words model. We express the query and document as a sparse word frequency vector, like the one hot vector. We usually do some sort of normalization for length. And here's an example. So like, let's say we have a query that says, what is NLP? We have a big vector of all of the vocabulary items that we might be accessing. And we turn this query vector into a frequency vector normalized by length. So we have 3 words in here. And so we get 0.33, 0.33, 0.33, et cetera. Then we have a whole bunch of documents. Let's say our first document said, what is life? Candy is life. The second one said, NLP is an acronym for natural language processing. And the third one said, I like to do good research on NLP. So this would also be normalized in some way. And so we would get what, and we would get is, and we would get candy. And this one is NLP is an acronym for natural language processing. So we would get NLP and we would get is. And then for this one, we would get just NLP because there's no is in there. So based on this, what we can do is we can find the document with the highest inner product or cosine similarity within that document collection. And if we do this, the first one is 0.165. The second one is 0.0825, and the last one is 0.0413. So does this seem like a good solution? Not really, right? Because the first one's about candy, and we want to learn about NLP, not candy. So in order to fix this, we use things like term weighting. I talked about this briefly maybe 2 classes ago when I was talking about TF-IDF and embarrassingly couldn't remember the formula for TF-IDF off the top of my head. But I have it right this time. So the basic idea is some terms are more important than others. So we want to upweight ones. In particular, we want to upweight low frequency words because they're usually more important for the content. So a common way to do this is term frequency in document frequency or TF-IDF. And so the term frequency is basically the frequency of the term in the document divided by the total frequency of the document. So that was essentially this normalized frequency here. And the other one is in document frequency. So this is the log of the total number of documents divided by the number of documents in which this term occurs. So if this term occurs in lots of documents, this fraction here will be close to 1, which means the log will be close to 0. If it doesn't appear in many documents, this fraction or this value will be very large here. Like let's say there's 100,000 documents and it only appears in one document, then this would be 100,000. And so we would get a very high upweighting of this. And we multiply the term frequency by the in-document frequency. The most common method for sparse retrieval, which is actually a really strong baseline and still used pretty widely, is BM25. And we basically do some additional smoothing. And so we have IDF, we have the frequency, and then we have some other, we have some other things in here where we're basically smoothing the frequencies so it's not quite so sharp. Like, for example, this is a very, like, if this appeared in only one of 100,000 documents, this would become very large, and this is a little bit more conservative with respect to doing that. So anyway, once we have these sparse weighted frequencies, we want to look them up efficiently. And the common way we do this is through something called an inverted index. And the way an inverted index works is we essentially have our sparse vectors. And so this is what our, this is saying like what and candy and is, etc. And we turn this into an index where we instead have the words. And we have all the documents where these words have non-zero terms here. And so what this allows us to do is this allows us to look up essentially document lists for each of these terms and do this efficiently. And if the document lists get very, very large, then even this is ponderous. So there are ways to optimize this. And I have not, like, honestly, in my entire career, I have not implemented the more efficient versions of inverted indices. I've implemented the very simple version of inverted indices. But the reason why is because we have engines like Apache Lucene and other things like this that implement these. And if you are going to be doing research specifically on retrieval, this is something you'll probably want to do. But I've never had to do it myself, which indicates that you also likely will not need to if you're working on NLP. Yeah.
Did you use like the blue score or rouge or something to do retrieval? Like sparsity?
Could you use blue score or rouge to do retrieval? That's a great question. Well, so yeah, it's a great question. Could you use blue score or rouge score? The follow-up is, isn't blue for generation? Isn't it a method for evaluating generation, essentially? There's a couple reasons why blue score or rouge score would not be the best method here. The first reason is it might actually be okay, but it's probably going to be very low for every document because your query is going to be like 3 words, right? And the documents are going to be really long. So blue score and rouge score essentially look for like very good match between the inputs and outputs. The other reason why is actually computational feasibility. So in order to do a blue score or rouge score, you would need to have some way of computing. And blue score and rouge score do things like compute 4grams. So you would need to index all of the 4grams in your corpus, and that might become computationally expensive. But yeah, it's a good question. Any other questions? Okay, so these are used very well. These are very commonly. These are very good baselines. If you're working on stuff that's out of domain, like not the domain that you have training data in, actually, these can beat everything. These can beat like all of the strong embedding-based models and stuff like that. So it's definitely something that you should be trying if you're doing any sort of retrieval. But the state of the art in most fields right now is dense retrieval. And dense retrieval contrasts to sparse retrieval, just like kind of an embedding-based classifier contrasts to a bag of words classifier. And the way it works is we essentially encode documents or queries and find the nearest neighbors. This can use out-of-the-box embeddings or learned embeddings. And so we have a whole bunch of documents. We encode all of them into vectors of some variety. And we have a query. And we take this query and we find the nearest neighbor in this big index. So the first question, I guess, is how, given a document or a passage from a document, do we get embeddings? I actually just realized I forgot to add a slide, so I'll explain in a second. But basically, let's assume that we have a sequence, and this sequence is like a sentence or a paragraph or a document or something like that. There's two common ways to get embeddings from this. The first way is to take the embedding of one token. So if we have something like a left to right language model, like most of the standard language models we use nowadays, Llama, Mistral, the OpenAI ADA model, anything like that, then we might just take it from the last token. Do people know why we take the last token here? Not a trick question. Yeah, because you've seen everything in the document. So it's the only token where you have all of the information from the document. Another method is to pool all of the tokens together. And so you just take all of the tokens and then you squash them together in some way, take the average. Both of these are used. I would say nowadays it's probably, my impression is that it's more common to take a single token. But I've seen both of them used. One big thing when we're calculating embeddings for sequences is what variety of model to use. I realize this is a little bit out of order, but one very common way to do it is to use a model that's based on bidirectional attention. I haven't talked very much about these models, but I will be talking about them a little bit more later in the class. But basically, these are models that were trained with masked language modeling or other varieties of loss that aren't strictly left to right. And that means they don't need to have masking from left to right. Instead, they can have bidirectional masking. So bidirectional masking means basically you don't implement the left to right mask when you're training the model. So previous tokens and next tokens can attend to each other. And this can be very useful in calculating kind of the semantics of tokens that are earlier in the sentence than later in the sentence. So I realize we haven't got a lot into these models, but that's the basic intuition here. However, these models were like super popular from 6 years ago until about 3 years ago or something like that. But recently, these models were good for like classification, for tagging, for other stuff like that. But now everybody wants to do generation and prompting and stuff like that. And as I mentioned in like the sequence modeling class, these bidirectional models are not very good for generation because you really need to generate left to right. And so most of our competitive models nowadays, nobody is training these huge bidirectional models. So all of our best models are kind of left to right models. So in 2024, starting in 2024, people have been focusing on getting good embeddings out of these kind of left to right models. And there are two representative methods that I'd like to introduce among all the methods that people have proposed. The first one is called LLM to VEC. And the basic idea is they take a unidirectional model and then they remove the unidirectional mask and they just mask in both directions, or they remove the mask so they can attend in both directions. And then they either just use the embeddings as is with this bidirectional mask, or they further train the model using kind of the same masked language modeling objectives that these other models use. Another paper, which is a paper by us, Jacob Springer, a PhD student in MLD, does something called echo embeddings. And the basic idea is that the main problem with left to right language models is that you aren't able to attend to things in the beginning of the sentence after you've seen the end of the sentence. So we demonstrated that you can just repeat the sequence twice. And if you repeat the sequence twice, then the things at the beginning of the sentence can see the words at the end of the sentence. And this greatly increases your accuracy of embeddings. So I think basically what this says is either way, when you're calculating these sentence embeddings, you want to have some way to attend bidirectionally, and both of these methods are, potential ways to do so. Cool. Any questions about this? Yeah. Is there any, like, you mean negative effect or? I mean, the accuracy goes way up with respect to doing retrieval tasks, and so does this one above. Yeah. The negative effects, I don't know if we really saw any negative effects, but we weren't looking for them really carefully. So, you know, but nothing super obvious. Yeah.
There a winner between these, like one of those form vector.
Yeah, I don't think there's a super clear winner. This number does report better results, but the numbers aren't like strictly comparable. The data is different, and the base models are not always exactly the same. So, yeah, it's not super clear. Yeah. Cool. Okay, so these are ways to learn good embeddings of sequences. And maybe before I go into the next point, I'd like to talk about what is a sequence in the first place. And usually when we are doing retrieval for models, specifically retrieval augmented generation systems, we want to be retrieving a chunk of text that is good enough to allow the model to essentially answer questions about that chunk of text. And so there's a number of options for how we could chunk text. The first one is sentence. The second one is paragraph. And the final one is like N tokens, where this could be like 512 tokens or something like this. These two are kind of like semantically meaningful units. These are not semantically meaningful units. But the problem is if you don't segment on like N tokens, what if you get a really long paragraph? Or what if you're dealing with a CSV file? Where do you find the paragraphs in a CSV file or other things like this? So there's a whole bunch of edge cases that make kind of like more semantic segmentation difficult. So in a lot of cases, people just like take N tokens, like 512 tokens, and then 512 more, 512 more. Or optionally, they might take 512 and take like overlapping windows like this to make sure that you get like contiguous contexts if the answer is like over the border here or something like that. So these are common ways of getting like the sequences that we want to be modeling. And I haven't seen any really conclusive evidence that one is better than the other, like empirically. Like some people say one is better, some people say others are better. Cool. Okay, so now that we have sequences, we have a base way of embedding. So we take a language model, we get an embedding for a sequence. We'd like to make it so it works really well for retrieval. And there's a number of ways of doing this. The most common way to do this is to select positive and negative documents and then train the model using a contrastive loss. And what I mean by this is usually we use something like a hinge loss where, or I wouldn't say usually, but like often we use something like a hinge loss where this is the score of the negative document. This is the score of the positive document. And we want to make sure that the positive document basically has a larger score than the negative document. And if that's the case, then this goes to 0 and our loss goes to 0. Other alternatives are to take the softmax and try to maximize the probability of the positive documents. Both of these are used in practice. So what do I mean by a positive document and a negative document? A positive document, you can obtain them in different ways. If you're doing it for search, like let's say you're working at a search engine company, a common way to get positive documents is through click-through logs. So if you have a query, you look at the thing that people actually clicked on and you treat that as a positive document. If you're working on something like RAG, there are different ways of doing this. One way of doing this is you actually have annotated gold standard documents. And so these would be documents that somebody said, this is the document that has the answer in it. Or if you don't want to annotate them, yourself, another way to get positive documents is to have an answer. And any document that contains the answer is treated as positive. Any document that doesn't contain the answer is treated as negative. So there's a bunch of different ways to do this. The gold standard, the way of getting gold standard documents is pretty important because just because the answer is included doesn't mean that, like, just because the gold standard answer is included doesn't mean that the document actually answers the question. It might be coincidental that that's also included. So to give an example, let's say the question is, when was Joe Biden elected president? The answer, or what year was Joe Biden elected president? The gold standard answer is obviously 2020, but there's a ton of documents that include 2020 that don't actually answer that question. So. Cool. So the net, yeah. So if there are multiple documents that are relevant for a query, actually this already takes that into account. Basically, what it tries to do is it tries to upweight the positive examples and downweight the negative examples, so it can upweight multiple positive examples.
Like put two documents together gives a relevant answer, but often
Yeah, okay, I see what you mean. So basically a multi-hop query where you need to retrieve from multiple documents. You know, that's a really good question. I think my impression about what they do is they treat both of them as positive, and they don't necessarily consider the fact that you actually get it right if you have both of them included. They just try to upweight both of them. But I'm not 100% sure. It's possible that somebody has thought about this before, but I can't think of any work that did that. It's a good question. Any other ones? Okay, cool. So then the next question is how to get negative examples. So the first way to do this is in batch negatives. This is a very simple, easy to implement way. You create a batch of queries and associated documents. And let's say we have one positive document for each query. That would mean that we would have this one is the correct answer for this. This one is the correct answer for this, etc. And so essentially you get a thing that's like a label space with all of the ones along the diagonal being correct. And then you can kind of assume that all the other ones in the batch are just not good answers. And this is a good, this is a fairly good assumption if you're picking all of these randomly and, there are very few documents that answer a particular question. You might get it wrong some of the time, but it's usually correct. However, a big problem with this is there aren't enough hard examples. So because you're picking these randomly, like most examples on the web are not hard. Like you're not likely to retrieve them from your models. So you'll get to the point where this just becomes way too easy of a problem, distinguishing between the correct ones and the incorrect ones. So another common thing to do is to do hard negative mining. And hard negative mining basically tries to find difficult examples. And so one way you can do this is you can take a baseline retriever like BM25, retrieve documents, find the ones that, for example, if it's RAG, find the ones that don't have the answer included in them and treat those as negative examples and append them to your batch. And so this gives you plenty of hard examples for each of the queries here. The problem with this, though, is hard negatives might actually be positive. So like, for example, let's say your answer to when was Joe Biden elected would be 2020. But it says like 2020. Or like you have 2021, you have an article from 2021 and it says Biden was elected last year or something like that. Like there's a number of ways that your judge of these validating that these are actually negative might not work. So this is actually quite tricky. It's not an easy problem. So cool. Yeah.
Are negatives in the queries very similar, but they're still false, or are they like very different? Like when you use BM25 in both, are they the most dissimilar ones, or are they?
Oh, these are the most similar ones that nonetheless are negatives. So you retrieve them with BM25 and then you try to find the documents that like don't include the gold standard answer for RAG or like weren't included in click-through logs or whatever your criterion for finding positive examples, it like doesn't match the positive example criterion. Yeah. Cool. So there's a bunch of methods for training these models. Just to give a few, DPR learns encoders based on BM25, hard negatives and in-batch negatives, like I talked about here. This is kind of a classic approach. It's relatively simple. You can look it up. There's also interesting other methods like Contriever, also a method that's used pretty widely. This proposes something called an inverse close task. And the way it works is you have a phrase and you try to retrieve the rest of the document based on the phrase. So it's kind of like inverse masked language modeling where you take a phrase from the middle and try to predict all of the other parts of the document. And then there's a bunch of other methods here too. Cool. So all of these methods, basically what they were doing is they were getting a single vector and using that vector to look up. Oops, sorry. Yeah, they were getting a single vector and using that vector to look up the documents. The reason why this is necessary is because we want to search over a very large database of documents. And that needs to be very efficient, especially if we're doing it over like the whole internet or something. So the way we do this search, so like just a reminder, we want to be taking the query and we want to be finding the closest vectors here, where the number of these vectors is like on the orders of 2 million or 2 billion or whatever the size of our document database or passage database is. So in order to do this, obviously we need a sublinear time algorithm. We need something that isn't linear in the size of our document database because that won't scale. So we have methods to retrieve embeddings in sublinear time. One common example of this is something called locality sensitive hashing. And the way this works is if you remember inverse indices, like an inverse index, basically an inverse index was mapping from a word in a sparse vector into all of the documents in the index. Locality sensitive hashing, basically what it does is it tries to turn a dense index into something that looks more like a sparse index. And so the way we do this is we have these embedding vectors. These embedding vectors in reality, they're like 512 dimensions or 1024 dimensions or something like this. But for visualization purposes, I just showed it in 2 dimensions here. And you draw planes in this space and you assign a value to everything that's on one side of the plane, a value of 1 to everything that's on one side of the plane, and a value of 0 to everything that's on the other side of the plane. So we have the blue plane, the red plane, and the green plane. And so everything that's above the blue plane to the left, or in this direction of the blue plane, in this direction of the red plane, and in this direction of the green plane, will get 1, 1, 1. Actually, there's no points with 1, 1, 1 here, but like this point up here is on the kind of correct side of the blue and green planes and on the wrong side of the red plane. So it'd be 101. So this allows you to convert basically dense vectors into binary vectors. Continuous vectors into binary vectors. And then once you have the binary vectors, now this is like a sparse vector that we had before. We can use an inverted index to look up the points in this space. So this is this is rather clever. I don't think I would have thought up this this method myself, but it's kind of nice. Another way to do this is through graph-based search algorithms. And the way graph-based search algorithms work is they essentially take our original space and then they find hubs in this space where these hubs serve as representatives. And if the number of hubs is sublinear in the overall size of the space, we can then essentially do a search for the hubs and have a hierarchical search where we first search for the closest hubs, and we search for the closest things within those hubs and stuff like that. So it's essentially an incremental search through the space. And if you do search one time, you could have hubs equal to the total number. So if n is the total number of points, you could have square root of n hubs and then square root of n points in each hub. So your search time, instead of being n, would be square root of n plus square root of n. So that converts it into O of square root of n algorithm. If you have 3 steps, then it could become O cube root of n, because you could then do cube root of n, cube root of n, cube root of n. So there are these algorithms too. And these are implemented in software like Vice, Chroma, DB, and other things like this. So the good news is, if you're really interested in this, you can do this, but you don't need to implement this yourself. You can just use existing software and it works reasonably well. Cool. Any questions here? Yeah. How do you decide the number of partitions? So I mean, you would have different considerations. You would want to pick things that maximize or minimize basically your mistakes and maximize or also minimize the time. In reality, I think it's pretty common to have a smaller, like not have a whole bunch of hierarchy and just do it in like 2 passes. And so if that's the case, then square root of n is ideal. I actually don't know exactly what's going on under the hood because, as I said, I haven't implemented this myself, and I mostly use libraries for this. But if you want to look into it deeper, there's lots of papers on that topic. So. Cool. Any other questions? Another thing that I should mention is this can be made a lot faster, even though it's approximate fast search, it can be made a lot faster by doing it on GPUs. So if you can fit this on GPUs, using GPUs makes it a lot faster. If you can't fit it on GPUs, you can put it on your CPU memory. If you can't fit it on your CPU memory, you can put it on an SSD. And each one of those will get a little bit slower, but all of those are included in any decent vector search library. So all of those are options. Okay, so as I mentioned, in order to do this sort of search, it's important to have a single vector for each database, or sorry, for each document that you're searching. And the reason why, or it's not important to have a single vector, but it's important to be able to encode the documents independently of the queries. Because if you can't encode the documents independently of the queries, you can't construct this vector database ahead of time. You would need to do it each time you have a query, and then that you don't get any of the efficiency gains. So this is the by encoder method where you encode all of the documents beforehand, then you encode the query, and then you do a vector search over them. The problem with this is very inaccurate because you need to, this is not the most accurate way of doing things because you need to encode the documents before you know the queries. So you need to, your document encoding basically needs to get all of the relevant information for any query possible. On the other hand, there are methods that use cross encoders where essentially you have the queries and the documents. You encode all of them together. And then in the end, you make a decision about whether this is relevant or not. So like a very simple way you could do this is you could append the query before or after the document and ask a language model, is this query relevant for the document? And the problem with this is this will not scale to your whole database, of course. But what you can do is you can retrieve like the top 50 or something like that, and then re-rank them and feed the top 50 into your final decoder or something like that. Any questions here? Okay. So there's actually a middle ground. And the way the middle ground works is it does token level indexing and token level of both the documents and the queries. And given the documents, instead of getting a single vector from the whole document, you get one vector for each token in the document. And now when you index the query, you also, when you index the query, you also get one for each token in the query. And then you calculate the maximal similarity of each token with each token in the database. So does this remind people of anything that we've done so far? Any modeling technique? What modeling technique do we use to calculate the similarity between tokens and, for example, an input and an output? Attention, yeah. So this is basically like the difference between a non-attentional model, where we need to compress all of the information in the sequence down to a single token, and attention, where we are looking at token by token correspondences. So this is really, really effective. Like all of the strongest retrieval models can do this, can do something like this. It also actually still works with vector databases because we're still encoding these separately. We're encoding the document tokens completely separately from the query tokens. And then only at search time do we do like 3 searches. If the query had 3 tokens in it, we would do 3 searches over all the document database. However, there's a huge problem with this, which is if you're encoding each token in the document, now you have 512 token documents or 512 token passages. You're using 512 times the disk space in order to store this huge index. And also, even though these approximate search methods are sublinear, they're still not, constant. And so that does increase your search time. And a representative of this is something called Colbert. There's like Colbert and Colbert version 2. These are relatively easy to use. There's also other methods, but this is a good one to start out with if you want to. Yeah.
When you do this encoding, do the 2 encoders need to be the same model? Or can they be like different representation spaces and it'll work as well?
Oh yeah, that's a great question. Do the 2 encoders need to be the same model? I've seen them all start from the same base model as far as I know, because kind of if you start from completely different base models, then you have a high, overhead of aligning those 2 models beforehand, but you don't need to have both be the same model. Like you can have both be the same model, but they don't necessarily need to be. Yeah.
Are the tokens encoded, like, do they have some sort of attention to the encoding itself, like before the maximum?
Yeah, so this query encoder will typically just be a standard transformer. Yeah. Cool. So another thing I'd like to talk about is kind of these are like the base of most retrieval models that you see nowadays. So either the bi-encoder method or this sort of like token level bi-encoder method. Most dense retrieval methods will use something like this. But there's also some variants on how you can do this. The first one is there's something called instructor embeddings. And instructor embeddings, basically the idea behind them is this is instruction tuning for embedding models. And so like just like we have instruction tuning for LMs, we can also do instruction tuning for these embedding models. And so the idea is if we have like who sings the song Love Story, we could have different instructions about how we embed this, like find duplicate. I guess I have a typo in the paper, questions, but questions. And it would generate things that are good for finding duplicate questions or retrieving documents from Wikipedia or classifying the questions topic. And so this allows you to pull out embeddings that are useful for particular tasks. Another thing that I've used myself in some of my research that is pretty effective is something called hypothetical document embeddings. And the way this works is you essentially take a query and you generate a hypothetical document for the query using an LLM, and then you try to look it up. And the reason why this is a really interesting and clever idea, I guess. So for instance, how long does it take to remove a wisdom tooth? We would say write a passage to answer the question. And you know, a model, it could be GPT or any other model, will write a passage that answers the question, with the idea being that if you have this passage, this would give you a closer match to the final passage that you want to retrieve than the query would. And so what this is kind of doing is this is outsourcing some of the difficulty of like doing semantic matching between the question and the final document to a large language model like GPT. And you only need to run GPT once. You don't need to run it over all of the documents. So it's also a bit cheaper. So I found this to be really useful when we're doing something that's like very out of domain for our embedding model. It seems to come up with terms that match reasonably well with the documents that we're trying to retrieve.
Should also explicitly train a model to produce good like search queries, right?
Yes, you could train a model to produce good search queries as well. Yeah. Yeah.
Typically, also when GPT sort of expands on the query, does it add in unnecessary information that might hurt the query?
So when GPT expands the query, does it add unnecessary information that could hurt retrieval as well? Yeah, of course. You know, it's completely hallucinating the document that answers the question. But I'll talk about another method that we did that's a little bit similar to this later. And there are some mitigating strategies for stuff like that too. Cool. Okay, so I've been talking a lot about retrieval methods. Next, I'd like to talk about evaluating retrieval briefly. And when we look at evaluating retrieval, we want to think about what's a good result. And it kind of depends on the downstream use case. So like what's a good result for humans and machines differs a lot. A good result for humans, we really need the relevant information ranked at the top of our ranking list because that's all human attention allows us to look at. For machines, it's much less obvious, especially now that we have much longer context models. It might be just that we need the relevant information somewhere in all of our retrieved data. So kind of the desiderata of these two things are different. Most evaluation metrics, I think, focus on the human case. So I'm going to talk about those a bit, but at the end, I'll also talk about the machine case. So ranking metrics, especially ones designed for humans, generally start with gold standard relevance judgments. The gold standard relevance judgments you can get in anyway, but they might be something like highly relevant, somewhat relevant, not relevant, just labeled by humans. They could also be like click-through rates or, you know, some other weak signal of relevance. So there's a famous metric for this called NDCG. It's kind of the standard metric. I'm going to gradually build up to it over the next couple slides. And the first part of it is cumulative gain. So cumulative gain. Also, another thing is retrieval metrics. Often we measure them at n, which is the size of the retrieval list that you generated. So cumulative gain at 5 would be the sum of all of the relevance that we get in the top 5 retrieve results. So we might get, for this, it would be 2 + 1 + 2, so we would get 5. Let's say we had a similar ranking where we put the best documents on top. Let's say we have 2 highly relevant documents and 1 less relevant document. We would still get 5, right? So this seems like a little bit of a problem, right? Because the first one here seems kind of obviously better than this one, or the one over here seems obviously better than the one over here, but they're getting the same score. So discounted cumulative gain, basically it gives a discount for each of the, as we go down the ranking list. And they kind of semi-arbitrarily chose 1 divided by log 2 I + 1. And that gives us a score. And so now the ideal ranking gets a higher score than the non-ideal ranking. Then finally, NDCG, or normalized discounted cumulative gain. Basically what this does is it makes sure that you don't get penalized for picking more good documents. And the reason why this might happen is here we have discounted cumulative gain at 2. It's 1.26. And here we have inverse discounted cumulative gain at 2. If we actually, sorry, this is not the best example because here discounted cumulative gain went up. You can actually come up with instances where discounted cumulative gain goes down despite the fact that you added a good, added a good document. But here we have discounted cumulative gain, and that should be, sorry, at 3. And we end up getting a higher score. But basically the idea is as long as you're adding new documents, you'll be getting a better score. New relevant documents, you'll tend to get a better score if you do this. You won't get as high of a bonus if you are only retrieving like fewer documents. So that's the basic idea behind this metric. There's also a couple of other metrics that are very widely used. One is called mean average precision. The way this works is you look at the precision, which is the number of good documents divided by the number of bad documents, number of total documents. So that's the definition of precision. And then every time you add a positive document until you have found all of the positive documents, you add a precision value, and then you take the average of these precision values. And so if you look at this, we ignore all of the negative ones. So we ignore this one, and we ignore this one. And then here we have a precision of 1 divided by 2 because we have 2 total documents and found 1 positive one. 2 divided by 3, 3 divided by 4. So this would add up to 0.638 if you took the average of all of this. One thing I should note is this doesn't pay attention to like highly relevant versus less relevant. You kind of need to decide whether something is relevant or not. So it doesn't work with graded judgments, but this is another metric that people use. So NDCG and MAP are both good for human judgments because they're kind of paying a lot of attention to the top of the retrieval list. One that's widely used in machine judgments or RAG systems, evaluating retrievers for RAG systems, is recall at n. And recall at n is basically just seeing if you get any positive documents after a certain point. So here in our first retrieve document, we don't have any. So the recall at 1 for this particular instance would be 0. Here, recall at 2 would be 1 because now we have a relevant document, and recall at all the higher values would also be 1. So basically, this is saying, like, how early do you get a relevant document in all of the instances? And then you would average that over all of your queries. So this makes a lot of sense for, like, let's say you had a RAG system that would get the answer right if you had if you ever had an answer in your n-best list. So that's another method that we can use. Any questions about these? Okay, cool. So now I want to move on to retriever-reader models. So these are kind of retrieval augmented generation models. The simplest method that nonetheless is used quite widely and probably would be a good baseline for your assignment 2 before you do any improvements is you just chain a retriever model and a reader model. And so you can use an out-of-the-box retriever, out-of-the-box reader. For example, your retriever, not for assignment 2, but if you were building, an actual system, could just be Google, and your reader could be GPT. And immediately, in about 10 minutes, you could have a retrieval augmented generation system that answered questions, and it would probably actually be pretty good. And all of the passages, you just concatenate them into context and hope that the system will do something with them. However, you, as good NLP engineers, you probably would want to know, other things you can do above and beyond this. And in fact, you can definitely get better accuracy if you do things above and beyond the standard methods. So another thing that you can do is you can be training the retriever and reader to improve accuracy. And so this is the first paper, or it's the main paper that did this in kind of like modern, with modern language models and stuff like this. It's actually also the paper that coined the name retrieval augmented generation, despite the fact that this idea has been around since before this paper. But basically, the way this worked is for the reader, they maximized the generation likelihood given a single retrieved document. So they retrieve documents and maximize the likelihood of generating the output given a single one. Another, for the retriever, they did something unusual. We don't do this very much nowadays, but it's still kind of interesting. And the way they did this was they maximized the overall likelihood by optimizing the mixture weights over the documents. And here is a general conceptual idea. So they have the query encoder. Over here, they encode the query. They do maximal inner product search or dense embedding search. And based on the dense embeddings, they get a score, a retriever score. They calculate a probability based on this retriever score, and then calculate basically mixture of these language models with each of the passages concatenated, and then generate the output token by token. And the equations look a little bit like this. You basically have, each time you calculate the probability of a token, you have the probability of the retrieved document Z given the query. And then you have the probability of the next token given the query and the retrieved document in all of the previous tokens. And so this gives you your final probability. And this is end-to-end differentiable, so you can use it to optimize both the retriever model and the reader model. And yeah, the probability of the retriever is based on embeddings. And basically you take the dot product, or sorry, you take the softmax given the inner product between the retriever, the query and the key embeddings, query and document embeddings. One issue with this is they actually calculated the you would like to be able to also optimize the document embeddings, but optimizing the document embeddings is very difficult because you need to rebuild the search index every time the document embeddings change. And so in this case, they only optimized the query embeddings and they kept the document embeddings fixed. Any questions about this? People need a moment to stare at this. It's okay. One really important thing here is the only reason why this the embedder is trainable for this is because this is included in the probability of the generation. So this is good for training this retriever model, but the problem is that you essentially need to generate one passage at a time. And that's a big problem if, like, for example, in the previous comment, we have like multiple passages that are necessary to to answer the questions. So this is rather limited. It's also rather complex. And that's the reason why we don't use methods like this quite as much anymore. Okay. Another thing I should talk about is training LMs with retrieved context. So as I mentioned, in this method here, we train the reader by maximizing the likelihood given a single retrieved document. But in reality, when we build models nowadays, usually we pass in multiple documents or multiple passages into the models. So there's other ways to train retriever models. The most common way to do this is just to retrieve a whole bunch of contexts and then train the language model to maximize the likelihood of the output given all of these contexts. And this has a long history. This was done in DRQA, where they retrieved from Wikipedia and trained a reader based on this. It was also done in Retro, where they did language model pre-training with retrieved contexts. So they actually did this over the whole, internet, basically. The reason why they were able to do this was because they were Google and they had lots of computers. And we don't do this anymore, even if you're Google and have lots of computers, because the kind of like table stakes for how much data you train on has just increased so much that even for Google or OpenAI or places like this, like pre-training with this sort of thing doesn't seem very feasible. Or maybe they are doing it and they're just not telling anybody, but I kind of suspect that they aren't doing this. Cool. Any questions here? Yeah.
Does it, like, why do we need to rebuild the indexes every time? We could do it after we have multiple documents.
Yeah, great question. So the question was, why do we need to rebuild the index every time? We could do it after we've processed multiple documents. So another thing that you could do is you could just do like one whole epoch through the data, or you could process 1 million documents and then rebuild the index and stuff like that. There are actually examples of doing this. Like there was a paper called Realm that did something like this, REALM. In that, they actually had this thing where they had a separate process rebuilding the index constantly as the model changed. And then they just swapped in the new index when that process got done. But it's basically just a lot of extra engineering work or downtime or something like that. So it's not as common to do, but it is theoretically possible. Great. Okay. So another thing that I want to talk about, I think the final thing, is retrieval granularity. And there's a question about when we retrieve inputs. So by far, the most common way to do this is to retrieve once at the beginning of when you start generating. And what that means is you get a query, you look up documents with respect to the query, and then you generate the whole output based on this. However, we've been moving towards kind of like more long form generation. We've also been moving towards like tasks where we have agents that do things in multiple steps. And if that's the case, then we don't necessarily want to only retrieve once at the very beginning. We might want to be retrieving multiple times. there's a couple ways we can do this, like generating a search token or searching when the model is uncertain, and I'll talk about both these in detail. A final method is things that look up every token. This is kind of the extreme case. So it's just like every single time we look up something to calculate the next token. And there are a couple ways to do this, including finding the most similar final embeddings from the model, and also doing approximate attention with nearest neighbor search. So the first method that I want to talk about is triggering retrieval with tokens. And this paper seems like a classic paper now, so it's hard to believe it's from last year, but there's a paper called Toolformer. And basically what it did is it generated tokens that allow the model to use tools. But one of those tools was essentially web search or calling an external QA system. And the way it worked is they basically prompted a language model and said, if you think, here are the tools that you have access to. If you think the tool would be useful in this case, feel free to use it, and then generate the next token. And so one of those is wiki search. So that allowed them to perform search over Wikipedia, where they would search Wikipedia for Brown Act, and it would return the first sentence of Wikipedia. And then based on that, they would then condition the following generations. And the interesting thing about this paper is it's basically unsupervised other than prompting the model about what tools exist. But the way they create training data for this is they use the tool, and then if the tool increases the likelihood of the following generation, they keep that as training data. If it doesn't increase the likelihood, they throw away that example. So it's essentially like, it's a version of reinforcement learning, right? They're taking an action, checking if the action was a good action or not, and then penalizing the model for taking that action if they don't. Cool. And then you can iteratively train like this too. You can get a model that's better at using tools. This is the method that is used. I don't know if this is exactly the method that's used in ChatGPT, but it is, at least on the surface, it seems like the method that's used on ChatGPT. And Andrei Karpathy, like shortly after he left OpenAI, wrote on Twitter that this is what they're doing. So that might be in violation of his NDA or something like that. But yeah, apparently this is kind of the method that's used there. Another method, this is a paper by people in my group, but it's called active retrieval augmented generation. And the way it works is it tries to generate outputs. And then if those outputs are uncertain, it will go and do retrieval. So for example, let's say we're generating an article about Joe Biden. We first generate the first sentence, and it says Joe Biden, born November 20th, 1942, is the 46th president of the United States. Every token in this generation, by some kind of confidence measure, is high confidence. If that's the case, then we don't need to do any search because we're pretty certain that the answer is correct. Then we generate the next one. And we have like Joe Biden attended the University of Pennsylvania where he earned a law degree. But the tokens in the University of Pennsylvania and a law degree have low confidence. If that's the case, then we are worried about this sentence. So we need to go and do retrieval to verify it. And what we do is we mask out the low confidence tokens. So we basically replace them with kind of mask tokens. And what that allows us to do is it allows us to search for like Joe Biden attended blank where he earned blank. And so this is kind of like the hypothetical document embeddings that I talked about before, right? We now have a sentence from a passage that looks like the sentence that we want to generate. And we find the most similar sentences in our retrieval database and condition on those. And we do this kind of like measurement every sentence at the end of every sentence, so we can generate a very long passage and retrieve information as necessary. Cool. So kind of a expansion on this is something called self-RAG. And the way self-rag works is it's pretty similar to Flare, active retrieval augmented generation. But there's a couple differences. The first one is it retrieves every time. So every time it retrieves nonetheless, but it retrieves multiple passages. Based on the different passages, it generates different possible follow-up sentences. Then it has a critique model, where the critique model says, oh, passage 1 is both relevant and supported. Passage 2 is irrelevant. It's saying something that isn't relevant to the original query. Passage 3 is relevant, but it's not completely supported by the evidence that you got in the retrieval result. And so based on this, it will pick the best one that gets the highest score according to this critique model, add that to the prefix, and then continue to the next one. So it basically allows you to, get very high confidence results for long form generation. Cool. Any questions about this? Yeah.
Measured by the model itself, or is it some sort of external?
Yeah, great question. So in Flare, is the confidence measured by the model itself? In this case, it is measured by the model itself. It's based on the probability of the tokens. Measuring confidence in models is really tricky. I haven't actually talked about it yet, but I probably should sometime here. Model probabilities are a tricky measure of confidence because like a law degree could also be like a JD, or there's a bunch of different ways to say the same thing. So it is a bit of a tricky thing to do.
Yeah, that was my follow-up question. If, say, the dates were wrong on when Joe Biden was born, but the model has high confidence because it's seen the data before.
Yep.
But the data itself was not right, then how does the method sort of make up for that?
In this case, the confidences need to be right, basically. I think one good thing about this is the confidences only need to be not overconfident, because it's okay to kind of like search too much, or it's somewhat okay to search too much. But yeah, confidence estimation, I should definitely think about talking about it, but I'm not going to get to it in the 4 minutes we have left today. So. Cool. Another thing that is important to know is ensuring the use of relevant context. So, of course, better retrievers make more relevant context, result in more relevant context. But even so, we can have lots of irrelevant context. So especially if we have like a hard cutoff that we should have 40 outputs or something like that, a lot of those might just be completely irrelevant. So there's a couple methods to do this. One method is to train a ranker to decide whether the confidence is relevant. And so you can just train a re-ranking model, and the re-ranking model, if it says it's not relevant, you just completely remove it and don't include it whatsoever. Another thing that one of the people in my group, Zora Wang, did recently is taking the retrieved passage and filtering it down to only the most relevant context using a kind of passage classification model. And that's really useful because, so our passages are 512 tokens, and very often 512 tokens is like way more than you need to answer the question. But it's hard to decide a priori how long it should be. So just empirically, this also results in quite a bit higher accuracy.
You could also probably see if the confidence improves, right? And then based on that, decide whether
Oh, probably see if we could see if the confidence improves based on this. We didn't do something like that, but we could, yeah, especially if the confidence metrics are good. Yeah.
Instead of doing this at runtime, if we just distill all the model beforehand and then index that, would that be...
Oh, that's a great question. So instead of doing this at runtime, what if we did this before indexing? I think that would be interesting, but it is quite possible that there's lots of things in 512 in this 512 confidence. Actually, I'm not introducing this paper in the slides today, but this is a great paper, so I'd like to introduce it. It's kind of older. It's called like 65 million probably asked questions and what you can do with them. And so basically what they did was they took a big knowledge base and they generated questions that you could ask about the knowledge base. And then they searched over the questions instead of instead of trying to align the knowledge base. So it's very much like HIDE, but it's in the opposite direction. You're generating the queries. I feel like you could probably combine this idea with, whoops, accidentally listening to iTunes. Sorry, guys. You could probably combine this with this distilling, where you would like generate a whole bunch of questions that could be asked about the passage and then distill down to the context. That's a good answer for that question or something like that. Yeah, great idea. So the final things I'd like to talk about are methods that retrieve token by token. So instead of retrieving every sentence or something like this, they actually retrieve relevant context for each token. A famous example of this is something called KNNLM. And basically the way this works is you retrieve similar examples and use the following token from them to form a separate probability distribution. And so, for example, we would have these contexts. We have this test context. We retrieve similar contexts, and then we find the closest, we find the following words for the similar context. And then based on this, we get a probability distribution over the next words. And then we interpolate that with the actual neural language model's probabilities. So it's kind of like, we talked about n-gram models, right? Like discrete language models. It's kind of like forming a discrete n-gram language model on the fly based on nearest neighbors that you calculate according to the embedding model from the language model. And then a final thing is token level approximate attention. This is also something from someone in my group, Amanda Birch. And basically what it notes is that attention is an inner product. And so attention, we're taking the inner product between the key vectors and the query vectors. So we can also create a large data store out of all the key vectors. And the way we do this is we process the input as a sliding window and then perform attention using a vector index. So we essentially segment the input into this sort of sliding window like this, create an index, and then attend to that index. And this allows you to attend to essentially an infinite amount of context if you want to. So this is another method that you can use for token level kind of retrieval. Okay,